All right, we're going to ahead and get started. I'd like to thank you everyone who is joining us today. Welcome to today's CNCF webinar, MultiCloud Kubernetes with Nodeless. I'm Paul Simões, CNCF ambassador and cloud specialist at Oracle. I will be moderating today's webinar. We would like to welcome our presenter today, Madhuri Yechuri, founder of LL2. Before getting started, just a few key items. During this webinar, we are not able to talk as an attendee. There is a QA box at the bottom of your screen. Please feel free to drop your question there and we'll get to as many as we can at the end. This is an official webinar of CNCF and as such is subject to the CNCF Code of Conduct. Please do not add anything to the chat or questions that would be in violation of the code of that Code of Conduct. Basically, please be respectful of all your fellow participants and presenters. Please also note that the recording and slides will be posted later to the CNCF webinar page at www.cncf.io/webinars. With that, I'll hand it over to Madhuri to kick off today's presentation. Welcome, Madhuri.
Thanks so much, Paolo. Thank you all for joining this session on hybrid and multi-cloud Kubernetes with Nodeless. We will be talking about the definition of multi-cloud and hybrid cloud Kubernetes and go over a couple of use cases where you could find multi-cloud Kubernetes to be a compelling fit for your workloads, and define Nodeless Kubernetes, walk through the implementation, some of the implementation details of Nodeless and how it satisfies some of the requirements of multi-cloud and hybrid cloud Kubernetes use cases. We'll go through a live demo of using Nodeless Kubernetes to achieve multi-cloud Kubernetes and walk through some of the caveats and work in progress items for multi-cloud Kubernetes, takeaways, references, and we'll have Q&A at the end. We'll also have a short Q&A after the demo to answer any questions. And if we have any questions unanswered, we will include it in a fact section before uploading the slide deck and the recording to CNCF website by end of the day. Multi-cloud Kubernetes is defined as a scenario where your control plane for your Kubernetes cluster is running on cloud provider A, and a subset of the pods that are deployed through the control plane are running on a different cloud provider B. For example, your cloud provider A could be AWS and your cloud provider B could be Azure. A subset of multi-cloud Kubernetes is hybrid cloud Kubernetes, where one of your cloud providers, for example, cloud provider A, could be on-premise. So you could have your on-premise Kubernetes running on vSphere cluster in on-premise data center. Your control plane is running on on-premise data center, and a subset of the pods that are dispatched through the control plane could be shipped to AWS or Azure or a different public cloud provider. Why would you want to implement or want such a situation? Take, for example, you have an on-premise Kubernetes cluster that is running on vSphere in an on-premise data center, and you have on-premise pods that are deployed to essentially VMs that are running on ESX servers. You might want to stretch this Kubernetes cluster across multiple cloud providers beyond on-premise data center. You might want to ship some pods to AWS or ship some pods to Azure, At the same time, you might not want to go ahead and deploy control plane on AWS or Azure and maintain, monitor, and update the characteristics of the control plane. You might not have the resources, time, or the interest to maintain this plethora and hundreds of control planes across various public cloud providers when you actually have a working control plane that you're happy managing on your on-premise data center. This allows you to focus on your core business instead of curating pet compute on each of the cloud providers. And you're also avoiding the proliferation of control planes across various cloud providers. One of the use cases is wanting to burst during peak workload. Let's say that you have your Kubernetes master that is deploying 1,000 pods to 10 worker nodes on on-premise data center. You've done your capacity calculation and you figured out that in order to run your stable state 1,000 pod workload, you need 10 worker nodes on your on-premise data center. You've raised your purchase orders and configured your cluster, and everything is working fine on the on-premise data center Kubernetes cluster. Let's say Black Friday comes around and your peak workload spikes from 1,000 pods to 2,000 pods. Now you don't have the time to go and raise purchase orders to procure the additional worker nodes to stick into this Kubernetes master in order to be able to take on this burst workload. It would be nice if you can burst the 1,000 extra pods to a cloud provider like AWS or Azure or any other cloud provider to take on this extra workload that's coming in during Black Friday. And once Black Friday passes, when you're back to regular operations, your 10 worker nodes on your on-premise data center are sufficient to run your 1,000 pods. So you would want to get back your footprint to entirely on-premise data center. So this is one of the use cases where it would be nice to be able to achieve a hybrid cloud or a multi-cloud scenario that is driven through a single Kubernetes master. Another use case is if you're running machine learning workloads where you have your data that's residing on a public cloud provider, but you don't want to set up a Kubernetes control plane across multiple public cloud providers. It would be good to be able to drive the machine learning workload learning phase through the master that's residing on your existing cloud provider, which could be an on-premise data center. What are the ways in which we can achieve such multi-cloud Kubernetes without having to initiate a proliferation of control planes that are spread across multiple cloud providers? Nodeless Kubernetes is one such way of achieving multi-cloud Kubernetes. Nodeless Kubernetes essentially presents a virtual worker node into an existing Kubernetes control plane. The virtual worker node is advertising very large capacity that's available for placement of pods to the control plane, but in actuality, it consumes very small capacity. The virtual worker node can be dropped on any existing control plane. Like, for example, your on-premise data center's existing Kubernetes plane can be configured to run the virtual worker node. The virtual worker node, when it presents this very large capacity to the control plane, if a pod comes in to the control plane and is scheduled on the virtual worker node, the virtual worker node under the covers looks at the pod's resource requirements, amount of CPU, vCPU, memory, storage, IOPS, network IOPS, etc., and provisions just-in-time, cost-effective compute for your pod on the cloud provider that it is configured to run the pods on. So the just-in-time provision pod, if you've configured to run on AWS, for example, the just-in-time provision compute could be an on-demand instance, a spot instance, or a Fargate launch type. The launch types can be either set manually, or you could ask the virtual worker node to pick the right launch type based on your resource requirements and your SLAs. The virtual worker node provisions the just-in-time compute node for your pod, and your pod is dispatched over to the just-in-time provision compute node. As long as the pod is running to the control plane, it appears as though the pod is running on the virtual worker node. And the pod functions like a regular pod. And once the pod terminates, the underlying compute node is automatically terminated by the virtual worker node. So think of compute nodes that come up and disappear on various cloud providers based on your pod life cycle, rather than an always on statically provisioned compute node that's hand curated by you. The virtual worker node in actuality under the covers is not a real worker node. It's simply a pod that can be scheduled on any of the existing worker nodes that are currently being managed by your control plane. The pod runs a virtual kubelet and cloud instance provider container. Virtual kubelet is a CNCF project, and cloud instance provider is an open source project from Elotel. And the virtual kubelet and cloud instance provider container is speaking kubelet API, and it tells the API server that it advertises to the API server that, hey, API server, I'm a worker node, I speak kubelet API, and I have this very large capacity that's available to me for scheduling. And the very large capacity that is advertised is configured through a config map. So you could say that I have thousands of vCPUs, terabytes of memory, hundreds of GPU devices, etc. So there is no, it can easily be dropped on any existing Kubernetes control plane, because it's simply a pod that runs as part of a deployment that can be deployed on any existing Kubernetes cluster. So if you think about what are the main differences between a vanilla Kubernetes control plane and the Nodeless supercharged control plane, the vanilla Kubernetes control plane is depicted in the top half of this slide, where you think of your worker nodes as large bins that have static capacity, and your pods are balls of different sizes that are being stuffed into these large bins. Let's say a small pod has 1 vCPU, 1 gig of RAM, a medium pod has 2 vCPUs, 2 gigs of RAM, etc. So you have quite a bit of wasted resources, because essentially you're doing bin packing, and the optimal bin packing is only possible if all of your pods are homogeneous types, and your pods are running for a predictable constant amount of time. With Nodeless, when you're supercharging your control plane with Nodeless, what you see is one large virtual worker node, which is presenting very large capacity to the control plane. And the large worker node is doing bin selection instead of bin packing, where you're getting the right sized bin that's provisioned just in time for each ball. So a small bin, a small ball gets a small bin, a medium-sized ball gets a medium-sized bin, etc. And once the pods terminate, the underlying bin is tossed automatically. So let's go ahead and see how this actually works. I have a mini cube on my MacBook that is running a Kubernetes master, and I have a virtual worker node that is provisioned deployed onto the Kubernetes master. And I've configured the virtual worker node to ship pods to AWS for the sake of the demo. I will create an Nginx deployment with one pod that's scheduled on the mini cube, and it will get shipped via virtual worker node to AWS. And I will scale the deployment from 1 pod to 3 pods. And we should be able to see that the extra 2 pods come up in parallel. So you're not scaling up one worker node at a time. You're scaling up in a much more agile fashion in parallel for scaling up compute for your pods. And once I delete the Nginx deployment, we should see that the footprint on AWS is back to 0. And once we're done with the demo, we'll pause for Q&A so that any questions about the demo can be answered right away. So here I have my mini cube that's running on my MacBook. And I have the one master node, and I have the virtual worker node, which is called virtual-kubelet. If I look at virtual-kubelet worker node, and look at the available capacity, it says that it has 20 vCPUs, 512 gigs of RAM, and 200 pod limit that is available to be scheduled on this virtual worker node. If I look at the pods that are running in kube system namespace, we see the virtual kubelet pod that is running. So this corresponds to a virtual kubelet pod that is deployed on the Minikube cluster, and the virtual worker node is, this virtual kubelet pod is running virtual kubelet cloud instance provider container that is telling the API server for Minikube that, hey, I have 20 vCPUs and 512 gigs of RAM that are available for scheduling pods, and I can run up to 200 pods. And the configuration for the number of resources that are available to be scheduled on the virtual kubelet node, it comes through a config map. So you can configure GPU devices and other devices as well if you would want to expand the capacity of the virtual worker node. So let's look at a sample Nginx deployment as a workload. I have the Nginx deployment that sets app to Nginx, and I want to schedule one replica. And the node selector for this replica is set to virtual kubelet. And I would want one vCPU and 2 gigs of RAM that needs to be provisioned for the Nginx pod. So let's go ahead and create Nginx deployment. And while the deployment is being created, if we look at the virtual kubelet config map, we should see that we have the cloud provider that is configured to ship pods to. And we also see the CPU and memory and pod limit configurations that are set for the as the advertised capacity for the virtual kubelet node. So if we look at what's happening under the covers, the Nginx, the one replica for the Nginx deployment would be scheduled onto the virtual worker node because this is the only worker node that's available for the control plane, and it has enough capacity to take on one vCPU and 2 gigs of RAM resource requirements for the Nginx replica. The virtual worker node is configured via the config map to ship pods to AWS. So the virtual worker node will look at your Nginx replica's resource requirements, and it will provision just-in-time compute for your pod, for your Nginx replica. And once the compute is provisioned, the Nginx pod is dispatched over to the just-in-time provision compute node. The just-in-time provision compute node can be of various flavors. It can be on-demand, spot, or Fargate. You can specify via annotation to your deployment which compute launch type you have a preference for, or you could let the virtual worker node pick the right compute launch type for your pod automatically. Once the compute node is provisioned, the pod is dispatched over to the compute node. If your application has strict startup time requirements, like for example, if you have a strict SLA of 5 seconds between the time you say create Nginx deployment and the pod needs to respond to Nginx curl requests, you can also specify a number of a set count of pre-warmed instances that are available to dispatch your pods to. What the pre-warmed instances enable you to do is they'll cut down the instance startup time, which varies from cloud provider to cloud provider. And also it varies based on the compute launch type flavor you pick on a given cloud provider. So if you would rather not wait for, let's say, a minute and a half for an EC2 on-demand instance to come up in order to dispatch your pod, you can specify the count of, let's say, 5 number of on-demand instances of type C4.large that would enable you to cut down on instance startup time at the cost of having to spend a little extra for the pre-warmed instance launch types. So once the instances are provisioned, the Nginx replica is dispatched over to the instance, and to the control plane, it will look like the Nginx replica is running on the virtual worker node. So let's look at the Nginx replica in my AWS console. And it's running in a T3 small instance type, which is the best fit instance type that honors the 1 vCPU and 2 gigs of RAM resource requests for the Nginx replica. And the tags of the instances that are provisioned just in time reflect the labels. So the Nginx deployment had app set to Nginx as a label, so that label appears as a tag. So it's very easy to do accounting and monitoring of the resources that are belonging to a certain Kubernetes cluster that are being dispatched in various cloud providers. There is also the name tag of the virtual worker node and the namespace in which it is running, and the controller ID for the virtual worker node. So you can easily perform accounting tasks as well. In this case, because I did not specify any affinity for a certain launch type, what we get is a de facto on-demand instance. Let's go down and see. We should see that it's running on a regular on-demand instance. So it's a normal on-demand instance that is running the Nginx replica. So if I go ahead and scale the deployment, let's get the deployments first. So if I scale the deployment for Nginx from 1 replica to 3, what's happening under the covers is we would get the 2 extra compute launch types for the 2 new Nginx pods. They are provisioned in parallel. So your scale up time, the time it would take for you to scale up to unexpected bursts in your workload, is the time it would take for provisioning a single cloud compute instance, because the scale ups are happening in parallel. The 2 new cloud instances will be provisioned again just in time, or you can set up a set of pre-warmed instances so you can cut down on instance startup time. And the 2 new pods should come up once the underlying compute launch types are provisioned. And the behavior is exactly the same whether you're shipping from on-premise data center to AWS, or if you're shipping from, let's say, AWS to Azure, or Azure to GCP, or any other cloud provider. So essentially what we are trying to achieve here is to realize our on-premise Kubernetes control plane being able to automatically ship pods to AWS or Azure or GCP or any other cloud provider. Let's go back and see whether all the 3 pods are up and running, and our 3 pods are up and running. Let's get the deployment. 3 out of 3 are ready. So if we go ahead and delete the deployment, once the 3 pods are terminated, the underlying compute launch type will automatically be terminated. So if I go back to the to my EC2 console and look at the instance that is out here, refresh the page, the instance is being shut down. So once your pods are terminated, because your burst capacity is no longer required, the underlying compute launch type is automatically terminated. So you get back to being 100% on your cloud provider A with 0 compute footprint on the other cloud provider. So let's verify that we are back to running 0 pods. So this is a very simple demo of shipping workloads from the Kubernetes control plane that is running on a Minikube on my MacBook out to AWS. And the behavior would look exactly the same if you'd want to ship from a Minikube running on MacBook to Azure or any other cloud provider as well. Some of the caveats for the Nodeless ecosystem as of now, Persistent volume support for the pods that are running on the cloud provider B, which is the foreign cloud provider, is not yet supported. It's work in progress, and daemon set support also would need to be added to Nodeless ecosystem, because currently the implementation and the interpretation of daemon set assumes that the daemon set pods are running on every single worker node. We'll have to and this is the result of daemon sets kind of evolving from an era where on-premise data centers were the default, and you wanted to have the daemon set pod running on these very large worker nodes. We'll have to reinterpret it in the context of Nodeless as to, would the daemon set pod really need to run on the virtual worker node, or does it need to run on each of the cells that the pods are being dispatched to via the virtual worker node. As far as supported cloud providers are concerned, multi-cloud via Nodeless and virtual-kubelet and KIP is functional on AWS and GCP. It's beta on Azure. If there is interest in consuming any other cloud provider, please let us know, and we'd love to add support for any cloud provider that you are interested in. I'm going to pause here for questions to see if the demo made sense, and if there are any open questions. I'll hand it over to Paulo.
Hi, Madhuri. Awesome. Very impressive with this. I want to learn more. I want to test. Right. We have some questions. Manish Kumar asked, is virtual work node a separated component in Kubernetes?
A virtual worker node is a deployment with a single pod that runs on, that's deployed via the control plane. So it is, it's simply another workload that runs in your Kubernetes cluster. Does that answer the question? Let me go back to the, let me look through the deployment for. So virtual worker node is simply a deployment with one replica. And the replica is running a virtual kubelet that is built with a KIP provider. It's running virtual kubelet that is using KIP provider under the covers. And this container essentially is speaking kubelet API. So it talks to it connects back to the API server, and it advertises itself as a worker node. So it's simply a pod that can be scheduled on any of your existing Kubernetes control planes. So it's not any separate component that needs to be explicitly configured in your Kubernetes cluster. So you can deploy it, for example, let's say you can deploy it on an on-premise Kubernetes control plane. You can you can create the deployment on an EKS cluster or a GKE cluster, etc. Does that make sense, Manish?
There is a second part of, yeah, he answered yes. The second part of Manish's question was, and how to provision a virtual work node and attach to Kubernetes cluster. You answered already, right? You already answered to show the Kubernetes deployment.
Yeah. So it is simply a deployment. If you would like to try it out, there are simple deployment scripts that are available in the KIP repo. The repo is linked in the slide deck that will be uploaded to CNCF site by the end of the day. The deploy directory inside KIP gives you a couple of options for deploying a simple Kubernetes cluster with on AWS or GCP, or with VPN for on-premise, for bursting from on-premise to AWS, for example. If you want a simple setup to try it out, you can use any of the Terraform scripts, or if you would like to deploy it on an existing Kubernetes cluster, you can use the manifest scripts inside the manifest KIP directory. I will link all of these in the slide deck that's uploaded, that will be uploaded to the CNCF site.
We have more on questions. Just a minute, please. From Sergey Pogrebniak. Sorry, Sergey. I don't know if I said correct. What is the security setup for cloud provider communication?
Yeah, we default to VPN or direct connect or whatever is your preferred method for securing the communication between the virtual worker node that's running on cloud provider A and the virtual worker node and the pods that are running on cloud provider B. You can also try out a simple setup with a VPN. VPN is one of the basic ways of securing the communication between your cloud provider A and cloud provider B. If you'd like to see how that works, the scripts for that and the documentation for that is under Terraform VPN directory in the Kip repo. So here's, for example, it's creating a VPC with a VPN gateway for AWS. So you can default to VPN or direct connect, or depends on your cloud provider A and cloud provider B. If you have strict requirements for a certain kind of security link between cloud provider A and cloud provider B, please file an issue on the Kip repo, and we'd be happy to see how that would work.
So I suppose that you use your always as just a complement for understanding. The security provisioning is about they are assuming that you are in the same network, because VPN create a same network, right?
Right. Yeah. Mm-hmm.
Okay. Thank you. The last question is from Adarsh Key. Does this mean there is one pod per node?
That's correct.
That's
Was there anything else to the question, Paula?
No, it's just this. Does this mean that there is one pod per node? It's a question.
Yes. So we kind of look at cloud compute from one of the fundamental concepts of Nodeless is we look at cloud compute as something that is needed for pods rather than a disjoint entity that is provisioned 6 months or 9 months ahead of time and waiting to run pods. So based on the pod lifecycle, compute instances come up. Again, one of the fundamental premises of Nodeless is there is one compute launch type per pod. The compute launch type could be of any of the flavors that are available from the cloud providers. So it could be, and on AWS, for example, your compute launch type could be an on-demand instance, it could be a spot instance, or it could be a Fargate. What we believe is that as consumers of pods, you shouldn't be worried about hand curating compute launch types on each of the cloud providers and trying to keep a list of what are the 100-something different types of on-demand instances versus spot pricing versus what's the latest and greatest on Fargate, etc. So we make it very easy for you to consume the right compute launch type for your pod based on the pod's SLAs and resource requirements. So having one compute launch type per pod is kind of falls along those lines of being able to honor our goals of being able to manage the compute needs of a pod on a pod-by-pod basis. Does that answer your question, Adarsh?
No question more. Thank you, Madhuri.
Awesome. So let's go ahead and look at some of the takeaways. Increasing adoption of Kubernetes on various cloud platforms is leading to proliferation of control planes and a lot of heterogeneous clusters spread across various cloud providers. It leads to a huge amount of operational overhead and also wasted spend. There is no need for you to create 1,000 different control planes for each control plane running 100 pods each, just because you want to try out a new cloud provider and you do not have, you would rather expand your existing control plane across various cloud providers than hand curate these control planes on various cloud providers. MultiCloud Kubernetes is an idea where we are looking to simplify operations of Kubernetes clusters or across various cloud providers by reducing proliferation of control planes. It hugely simplifies multi-cloud capacity planning because you don't have to worry about hand curating, maintaining, monitoring your cluster auto-scaling knobs for your worker nodes and worry about how does scale down work. And also have to worry about, there is a newer, better, cheaper cloud provider in the market. How do I adopt this cloud provider in a very quick and agile fashion without having to provision control planes across various cloud providers? Nodeless Kubernetes is one way of achieving multi-cloud Kubernetes. Nodeless Kubernetes uses the two open source projects, virtual-kubelet, which is a CNCF project, and KIP, which is an open source project from Ilotle, and both of them provide a low friction path towards achieving multi-cloud Kubernetes. Everything spoken in this slide deck and demonstrated in the demo, all of that is doable with the open source versions. If you are curious to try Nodeless, check out the KIP repo. There are provisioning scripts, as mentioned earlier, while answering the Q&A questions. There are provisioning scripts for deploying a Terraform environment for VPN, using VPN, and for GCP as well. Check out the virtual-kubelet project, which is a CNCF project, and check out KIP. There's a ton of Nodeless reading materials on the Ilotle blog on Medium. Check them out if you're interested as well. If you have questions, please feel free to write to me or file an issue on the KIP repo. We hang out on virtual-kubelet channel on Kubernetes Slack. Feel free to pop in and ask any questions that you might have as well. Thanks so much to Ilotle Engineering, Brendan Cox, Vilmos Nebahoy, and John Roman for helping put together most of the code base and the scripts that were demonstrated in this session. Ria Bhatia and Brian Goff from virtual-kubelet team and CNCF marketing team, thank you so much for setting up this webinar and making it such a smooth process. And thanks to audience, Manish, Sergey, Adarsh for your questions. If you have any further questions, please feel free to ask them now. We will include the responses to any unanswered questions in a fact section in the slide deck that will be uploaded along with the recording to CNCF website by the end of day today. Thanks.
Madhuri, we have more 3 questions. I think that we have time. Could you proceed?
Yes, yeah, please.
Yeah, sure. From Manish Kumar again. Thank you, Manish, for questions again. In case of direct communication to cloud provider, where I will be storing cloud provider secrets? Is this similar the way we store secrets for a custom deployment?
The cloud provider secrets, as in the cloud provider credentials for the accounts, the VPC and security groups that you would want to consume on cloud provider, all of them are coming in through the config map and secrets configured on your original Kubernetes control plane. So all of that will be stored on the control plane that is the main control plane that is driving the scheduling of the pods. If my understanding of the secrets is incorrect, Manish, please let me know if there are any other secrets that you're talking about.
He got it. He got it. It's okay. Thank you.
Sure.
Daniel Kayson asked, can you have multiple virtual pods where the difficult virtual pods can be mapped to different public providers?
Yes, for sure. Yeah. So that is one of the main motivations for developing Nodeless, is that we would want you to achieve something like this, where you have a single cloud control plane and you have some pods running on, say, AWS, some pods on on-prem, some pods on Azure, some pods on GCP, or maybe Oracle Cloud in the future. So you can have multiple virtual kubelets that are dispatching pods to various cloud providers. So you have one cloud provider that's configured per virtual worker node. Let me show you a picture. So you have one cloud provider that's configured per virtual worker node, and you can run multiple virtual worker nodes, because at the end of the day, they're simply pods. So you can run multiple virtual worker nodes that are dispatching pods to various cloud providers. A subset of that question is you can run multiple worker nodes that are dispatching pods to multiple availability zones within a given region, if you want to do multi-AZ failover HA scenario as well. So the base unit for a virtual worker node is a single region, is a single zone in a single region for a single cloud provider. The virtual worker node is a very lightweight pod, so you can run as many pods as you want to ship to various cloud providers, various regions, etc. Does that make sense?
Very, Carlos. Madhuri, there from this question, we can give some choose preferable cloud provider, like something like which one is more expensive than others, so I will choose the more cheap, something like this. We can choose this or give it. So
yeah,
it's
that's
possible.
Sorry, is that the end of the question, Paulo?
No, we have more one question. Yes, yeah, it's my question because based on your explanation. Sorry, but we have more one question from any tragic that is, does Rancher's key 3F low footprint lightweight optimized for ERM support Nodeless virtual concept?
Let me address the first question. I couldn't hear the second one clearly, so I might request you to repeat it. So for the first question, yes, you can set affinity for a certain cloud provider, which is something that can be configured from your Kubernetes control plane itself. So if you have, let's say, one virtual kubelet for AWS and one virtual kubelet for Azure, they simply appear as nodes, worker nodes to the Kubernetes control plane. So we can enable you to define policies as to having an affinity for a pod to a certain worker node based on SLA metrics like cost or provisioning times or any other constraints that you might have. Like, for example, what is the cheapest cloud provider at the moment for running my GPU workloads? So you can express these SLAs as node constraints via the Kubernetes control plane, and that will drive the dispatching of the pods to the worker nodes that are associated with each cloud provider. So that's something that is a very compelling use case for Nodeless, because being able to switch between various cloud providers via a single control plane in a programmatic policy-driven way is something that's super useful for you to, again, enable you to focus on your business instead of curating pet compute on each cloud provider. Paolo, could you please repeat the question about Rancher? I didn't catch it completely.
Yes, it's does Rancher's key 3X that is optimized for ERM support Nodeless and Nodeless virtual concept? The question is if key R3 support this concept of Nodeless and virtual.
Key R3, I'm familiar with Rancher, but I'm not familiar with the product Key R3. So let me look it up and I will respond to it as part of FAQ in the slide deck. But Rancher itself, since it is managing Kubernetes control planes, any Kubernetes control plane can be supercharged to Nodeless because the virtual worker node is simply a pod that is dispatched to the control plane. So you should be able to run virtual worker node on any Rancher managed control plane itself. Let me look at Key S3 and update and respond to the specific details of the question in the slide deck as a follow-up.
Okay, excellent. No, we don't have more questions. I want to thank you so much, Madhuri. It was some great presentation. We learned a lot. We have much more to learn and use with this. Very, very cool. Thank you so much. All right. And that is all the questions. Thank you for joining us, everyone. The webinar record and slides will be online later today. We are looking forward to see you at the future CNCF webinar. Have a great day and keep safe. Bye-bye. Thank you.